We will continue with our topic on coastal protection. Right now we'll look at shore parallel offshore structures. Here we have a series of segmented breakwater which are designed to run almost parallel to the shoreline but is located offshore. These breakwaters created a seaside and a lee side whereby the breakwater dissipates the incoming wave energy such that the shoreline is relatively protected with calm water. Of course, not all shore parallel offshore structures come in series. In some cases, they may be a single breakwater which is located offshore but parallel to the shoreline. We recall that when we have an oblique wave that incident on a shoreline, the wave will create longshore transport, and thus we will have sediment moving in the direction along the shoreline. However, by introducing a shore parallel structure, what happened is that part of the energy would have been reflected or dissipated at the structure such that the lee side here has relatively calm water, and that would means that the lee side here will have less energy to induce the longshore transport. Due to that effect, the sediment which is carried along the shoreline may tend to be deposited in this sheltered region on the lee side of the breakwater, and as a result of that, the shoreline may evolve over time. For example, in this case, assuming that this is the original shoreline which is almost parallel to the breakwater, eventually the shoreline may bulge outwards towards the structure over here because this part is relatively calm and the sediment now becomes accreted or deposited in this region. Meanwhile, let's say if this section has no obstruction and the incoming wave can reach the shoreline, then there is a tendency for this part of the shoreline to be eroded. And so we see a profile of the shoreline to now change into a wavy patterns like this. This part of the shoreline which grow towards the breakwater is known as a salient. The volume of sand that may be trapped on the lee side of a breakwater in the salient depends on the length of the structure, depends on how far the structure is located from the shoreline compared to the width of the surf zone, and also depends on the amount of energy that is dissipated or transmitted. Now, one thing to also take note is that due to the concept of sediment budget, if there is a salient growth, then that usually must be accompanied by a down coast erosion. What do we mean by that? For example, here we have a series of segmented breakwater. We see that each of the breakwater has a salient behind them. Even if there is only one segment of the breakwater, the same concept described here will apply. Basically, what happens is the littoral drift brings sediment from this direction, but because of the calm region created by the breakwater on its lee side, the sediment are deposited to form the salient. When that happens, the down coast side is deprived of sediment. That means the down coast side right now has less sediment input. When there is less sediment input, it gives the down coast side more capacity to carry extra sediment, and that is the reason why there is a tendency on the down coast side to experience erosion in order to make up for the deficit in the amount of sediment in the flow. If the salient continue to grow outwards towards the breakwater, then it may be a point whereby the salient actually becomes attached to the breakwater, and in that case we refer to it as a tombolo. However, a tombolo can also grow naturally between a shoreline and an offshore island, whereby it is defined as a deposition landform in which an island or breakwater is attached to the mainland by a narrow spit or bar. For the case of a natural island, which is connected to the mainland by a tombolo, it is known as a tie island. Based on our previous discussion about the littoral drift in a longshore direction, salient will always grow on the lee side of a breakwater, but not necessarily the tombolo. Right now, let's look at this figure, whereby there is this breakwater with a length of L sub b, located at a distance of Y sub b capital from the original shoreline. The incidence wave is normal to the shoreline, such that when it reaches the breakwater, it is reflected or dissipated, so that the lee side is only subjected to the diffracted wave from both ends of the breakwater, and so the lee side is relatively calm and a salient is able to grow, and the shape of the salient here is more or less dictated by the shape of the diffracted wave. Generally, tombolo formation can be avoided if the length of the breakwater is less than its distance from the shoreline. However, tombolo can form under these two rules of thumb. In the first case, if the breakwater is located closer to the shoreline than the breaker line, assuming that this is the breaker line and this is the distance of the breaker line from the original shoreline. In this case, the breakwater is closer to the shoreline than the breaker line. Tombolo will form if the distance of the breakwater is less than half the breakwater length. On the other hand, in another case where the breakwater is located further away from the shoreline compared to the breaker line, for example in this location, which is further away from the shoreline than the breaker line, in this case the tombolo is still possible to grow or form if the distance of the breakwater is somewhere between 1 to 2 times the breakwater length. These are rule of thumb that we can use to design or determine the suitable location of our breakwater, as well as the length of the breakwater to be used. In some cases, our design will want to avoid the formation of tombolo. On the other hand, in other instances, we might want to design in such a way that we actually want the tombolo to be formed, depending on our design functional requirement. Let's now look at this particular example. It is desired that the salient behind an offshore breakwater only extend offshore 20% of the distance to the breakwater or less. Here, the distance of the breakwater is this. This is the original shoreline. We're going to allow the salient to form to the extent whereby the salient amplitude extend beyond the original shoreline only 20% of the distance towards the offshore breakwater, so that ys over yb equals to 0.2, where ys is the salient amplitude as shown here. If the length of the breakwater LB is 600 feet and a single breakwater is to be used, how far offshore should the breakwater be located? So how far can it be located? What is YB? In this particular case, we notice that we are given a graph here which provides the correlation between the ratio of ys over yb to the ratio of yb over lb. So where does this graph comes from? Most likely this is from a laboratory experiment in a basin whereby we have set up the shoreline and the breakwater, and the shoreline is formed using suitable sediment material representative of the site. We have a wave maker that generates the incoming wave that representative of the coastal climate on site, so that we can observe how the salient form over time and the amplitude of the salient can be measured. In fact, the correlation obtained has also been summarized in an equation form. We can see from here that as YB over LB increases, that means when the Y is much larger than the L by 6 times, for example, when the breakwater is much further away from the shoreline compared to its length, then the ys over yb will be almost 0. The salient may not even be formed if this breakwater is located so far away. Of course, we don't normally locate the breakwater very far away from the shoreline because it will be very costly to build a breakwater in deep water. Meanwhile, if YB or LB is a small number towards the left of the graph, that means if the breakwater is much closer to the shoreline, then we notice that YS over YB becomes larger and larger, which means that the amplitude of the salient may grow to 30%, 50% of the distance to the breakwater, and of course in the limiting case, ys over yb will equals to 1, meaning that a tombolo will form. So in this particular case, we are going to look at ys over yb equals to 0.2, and we read from the graph or calculate from the equation, we obtain yb over lb to be approximately 2.1. So based on this correlation, we can then calculate yb to be at least 1,260 feet away from the shoreline. The further it is away, then the smaller the salient will be, because we don't want the salient to be more than 0.2. Can be less, but not more than. So the distance of the breakwater from the shoreline can be larger than this value, but not less than this value. Let's say it is not desirable to construct the breakwater so far away from the shoreline because the water depth is too deep and the breakwater will be too expensive. Let's say the closest or the furthest we are able to build the breakwater at a reasonable cost is at YB equals to 1,000 feet from the shoreline. Then if we still want to limit the salient to only 20%, then you notice that we can use the same ratio here to recalculate, but this time what we get is by setting YB equals to 1000, we obtain the length of the breakwater, which must be 476 feet or less. Cannot be more, because if it is more, then the salient will be larger than 0.2. So in this case, presumably, if we are going to construct the breakwater at a fixed location using the same criteria, we then determine what is the length of the breakwater allowable. In the earlier slides, we have already looked at how the length of the breakwater and the distance of the breakwater from the shoreline can be determined. Here we are going to look at segmented breakwater, which is typically used to protect a long stretch of beach while still permitting a certain degree of wave transmission. For segmented breakwater, the gap between two successive breakwater should be designed such that it is typically larger than twice the incoming wavelength. Generally, the ratio of the gap compared to the wavelength will determine the amount of energy transmitted. The larger the gap, the larger the energy transmitted, and thus the lower the protection. This figure here is taken from USACE's Coastal Engineering Manual, which shows a compilation of the observation of tombolo and salient formation at various coastal locations in the United States. On the top left is no sinuosity, meaning that the coastline has not responded to the offshore breakwater, and thus there is no salient, and there's also no erosion. Otherwise, in the middle region, salient formation can be observed. So in conjunction with the salient, we also describe it as a form of sinuosity, which means that the coastline will show bulge and depress alternatively along the shoreline, corresponding to a location which is on the lee side of the breakwater and which is exposed to the open sea. Whereas on the lower right, we have observations of tombolo formation. Now, if we look at the figure more closely, the vertical axis gives the ratio of YB over DB. YB is again the distance of the breakwater from the shoreline. DB is the depth of the breakwater. Whereas on the horizontal axis below, we have the length of the breakwater compared to the gap between breakwaters. So these are variable information that can only be compiled over a long time period and over observations from many different locations, which provides variable information for engineers to evaluate their design.